Hello, today we are going to look at alternating series. And so far, really all we've focused on are series of positive terms. And today, an alternating series that we're going to talk about is a series whose terms are alternating between positive and negative. So let's look at an example of something that we already know. We already know about the harmonic series, which is the sum from n equals 1 to infinity of 1 over n. And we know that these terms, if I were to write out these terms, I would have 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6. You get the idea. And what do we know about this? Well, we know this series is a diverging series. The harmonic series is a diverging series, a p series, where p is 1. So we know that. Now, if I want to make the series signs alternate, meaning instead of being 1 positive 1/2, I want it to be 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5. You get the idea. So I'm going to minus plus all the way through. What would I need to do? How would I need to change this series? So if we're still going from 1 to infinity, this is still going to be over n, but how do I get that alternating piece? If you remember, we can take -1 and raise it to the not n power, although that would work, but that would start with a negative first. But if we do n plus 1, that would give us our alternating series. And let's think about the sums of these series. Let's think about these partial sums here. If I take the first partial sum, that's silly, that's just 1. But if I take the second partial sum, I'm adding 1 and negative 1/2. So we get 1/2. And if I take the third partial sum, I get 1 minus 1/2 plus 1/3, or positive 1/2 plus 1/3, which is 5/6. And if I take the fourth partial sum, I get 5/6 that I had before, and I'm going to take away a fourth. And if I do 5/6 minus a fourth, I get, that'd be 7/12. So let's think about what this might look like if we were to draw these partial sums on a graph. Well, we'd start at 0, and we'd go to 1. And my first partial sum would be 1. And then my second partial sum would be 1/2. That'd be partial sum 2. And my third partial sum would be 5/6. And my fourth partial sum would be 7/12, so just above a half. Oops. And my fifth partial sum, if we keep going, and it would be just a little bit less than 5/6, but more than 7/12. And what we see is that this is oscillating, right? And we're going to keep getting closer and closer to a fixed number. Now, I'm not really concerned about that fixed number right now, but what it does show is that an alternating series may converge, whereas the same series that's not alternating diverges. So we have something called the alternating series test. And the alternating series test only tests convergence, but what it says is that if we have an alternating series, it will converge if 3 conditions are met. The first is that the a sub n, the part without the alternating, is always positive. Basically, we look to see that the series alternates. If it alternates, the a sub n expression will always be positive. And we can tell that it alternates because it has this -1 to the n, or -1 to the n plus 1, or even -1 to the n minus 1. The next condition that needs to be met is that the limit as n approaches infinity of a sub n equals 0. Okay? This is different, but recall, we have what we call the divergence test. And if you recall, and I'm going to write it on the side, that if we take the limit as n approaches infinity of some a sub n and it doesn't equal 0, then we know the series diverges. We can't use it to prove convergence, but we know if it doesn't equal 0, it diverges. Well, I'm showing that it does equal 0. And so it's going to be a little bit different. So really this passes the divergence test. And then what we need to show is that any term and the term after it would be less than. So the series is decreasing. Now, there's a couple words of caution. This does not say that if the limit as a sub n equals, or if it doesn't equal 0, the series diverges. That is not the case. The alternating series test will only show convergence. It does not test for divergence. What it does say, I think this is supposed to say does say, what it does say is that if the limit as a sub n the limit as n approaches infinity of a sub n, if it doesn't equal 0, then the series diverges by the answer test. But we can't use the alternating series test to prove divergence. Well, let's look at some examples of how we apply these three conditions. So the first thing, it does tell me whether to just determine the series converge or diverge. So the first thing I'm going to look for is whether or not the series is alternating. And I see this -1 to the n. That indicates it's alternating. Therefore, the first condition has been met. It's alternating. The second condition that I'm going to need to meet is that the limit as n approaches infinity of just the part that is not alternating. So we ignore the alternating part. If I take the limit as n approaches infinity of this part, 1 over n squared in mine, I want to show that it equals 0. Well, it in fact does equal 0 in this one. And then what I need to show is I need to show that any term is less than the term before it as n goes to infinity. Now there's two ways I can do this. The first, and the one that might make the most sense for this problem, is just substituting into our a sub n term n plus 1. And my goal is to show that when I substitute in an n plus 1, it is in fact less than the term before it. And of course we know if we plug in a number here, this number will be greater in the denominator, but that actually makes the whole number smaller. So this is in fact true. And so I've met both conditions, and therefore I can say by the alternating series test, this converges. Okay, that's different than other tests because I have to know it's alternating to be able to use this. Now, I told you there were two ways we could show that this was in fact decreasing. One way that I can do it, just in case, is I can always use derivatives. And if I take the idea that the derivative with respect to, in this case, I'm going to use x, we'll do 1 over x squared instead of n. If I take the derivative of that nth term, okay, and the derivative of this would be, well, this would be, if you want to think about it like this, the derivative of this would be negative 2x to the negative 3, or we'd have negative 2 over x cubed. And for all x's that are 1 and greater than 1, this will be negative the whole time. Well, let's think about it. If it's a derivative and it's negative, what does that mean about our original function? It means it's decreasing. So if it is really hard to show this, or it's not very clear that it's less than, we can always use the idea of derivatives to show that it is in fact decreasing. So why don't you hit pause and try this next one? All right, hopefully you had a chance to look at this next one, and we can see that I can use the idea of alternating series because of this. So this is in fact an alternating series, which is going to allow me to go through the rest of the process. First step, alternating, check. We've got that. Now my second step, is the limit as n approaches infinity of n squared over n cubed plus 1 equal to 0? Well, if we use the idea of relative growth, we can see that this will in fact be 0. The denominator is growing at a quicker rate, and so therefore it is 0. So second condition is met. Now we need to prove the third condition is met, and I need to show that any term is less than the term before it. So if I use n plus 1, and can I say it is less than n squared over n cubed plus 1? If I plug that in, can I say this is true? And the answer is yes, I can say this is true. Even though my denominator or my numerator is growing as well, my denominator is still growing bigger than my other denominator, and so therefore this will in fact be decreasing. So therefore, since all three conditions have been met, this converges by the alternating series test. And so I'm going to leave it to you to prove the next two, C and D. They are both converging by the alternating series test, but you can go ahead and prove those. Let's talk about alternating series error bound. What we know is that for some convergent alternating series, the partial sum is a really useful way to approximate the actual sum of the series. But obviously there's going to be some error because the partial sum cannot actually be the actual sum. And so what we call that error is the remainder. Now the remainder looks like this. We say the remainder of the nth term equals the actual sum minus the partial sum at n. So this Rn refers to our remainder, or our error. This S is our actual sum, and this S sub n is our partial sum, our nth partial sum. And so I'm going to show you an example of what this might look like here in a moment, but just know that our error is the remainder, the part that's left over of our alternating series. Now, if we have a convergent alternating series, then the absolute value of the remainder involved in approximating the sum is less than or equal to the first unused term. Now, here's what that says. That says that if we find our error, this is our error, this is our remainder, the error will equal the remainder, they're the same thing, and it will be less than or equal to the next term. That's what that phrase says. So let's think about it for just a moment. Ignoring the problem that's right here, I just want you to think about this. Do you agree that if I have some actual sum, it's equal to a sub 1, let's do this. If I write out all the terms of my series, that would need to be a plus. It would look something like this, right? And then we just keep going. This piece right here is called my actual sum. Let's say I use the fourth partial sum as my approximation. So this is my partial sum. This would be S sub 4. The remainder from here all the way back, this remainder is my R sub 4. And so what this phrase says is that my remainder, this entire quantity, needs to be less than or equal to my fifth term. Why? Well, think about adding these up. If I add this and I take away the next term is decreasing, so it's still not quite as big as a sub 5. So I'm taking it away, which gives me still a positive number. But if I add back a sub 7, it's a little bit less than a sub 6, but it does make the value of this whole thing more positive. And then the next term makes it a little bit, we take away a little bit less, but the value is still positive and we just keep going. No time in this will these numbers add to be more than a sub 5, the next term. Okay, so this allows us to determine an upper and lower bound for our sum. So let's look at the series that we're given. First of all, it needs to be alternating. We already know it is. We know it's convergent because we did this one in the first example. And so if I look at the terms of my series, of this series, we have -1 to the n plus 1 over n squared. My terms would be 1, minus 1/4, plus 1/9, minus 1/16, plus 1/25, minus 1/36, plus, right, we just keep going. Okay, if I want to find the sum using 4 terms, I'm looking for the partial sum, S sub n. That would be this right here, S sub 4, my 4th partial sum. And if I find this sum, the value of this, if I add all those terms together, is going to be 115 over 144, which is roughly 0.7986. Now, the remaining part of this part is my remainder. This is called R4. And what I know is that the remainder needs to be less than or equal to 1/25, which is roughly 0.04, which is exactly 0.04, sorry. So my remainder will need to be less than that. Now, what I also know is that this remainder will need to be positive. Why? Well, this first term's positive and I'm subtracting something that is not as big as 1/25. So my number remains positive. And then my next term that I'm going to add is going to be 1/49. So I'm going to continue to add a positive number, and the next time I subtract something, it won't be quite as big as what I've just added. And so it has to be a positive number. So what I can say about my error, what I can say about the error for this is that my actual sum would need to be 1/15 over 144 plus 1/25, and it could not be, and it needs to be greater than, needs to be greater than 1/15 over 144 plus 0. The lowest I could go with that error would be 0, and the highest that I could go would be 1/25. And so if I combine these two, if I find their decimal places, I know that the actual sum falls somewhere between these two numbers. And that's just me typing those in my calculator. So these are my errors. These are the bounds of my error based on the 4th partial sum. Now let's think about this just a little bit. The more and more terms we use, the remainder is going to be smaller, meaning my error is going to be even smaller. So the more partial sum I use, S sub 6, S sub 10, S sub 100, I know that my error is pretty small. Now, how would I figure that out? Well, here's another example. How many terms must I have to have an accuracy of 0.01? Well, what this says is that my remainder needs to be less than my next unused term. Well, having an accuracy of 0.01 says that my next unused term needs to be 0.01. And so therefore, what I know my remainder needs to be is 1 over n plus 1 squared, and that needs to be less than or equal to 0.01. Now, solving this one, I might multiply by 100 times n plus 1 squared to get 100 is less than or equal to n plus 1 squared. Now, it is possible that this is not able to be solved algebraically. Sometimes when we have these problems, we have to just figure out what term of our sequence gives us a number that is less than or equal to the accuracy that we're looking for. And if I go through and solve this, I get 10 is less than n plus 1, which means n needs to be greater than or equal to 9. So here's what this says. As long as I use some partial sum of 9 or bigger, so S sub 9, S sub 10, S sub 11, etc., my partial sum will be within 0.01 of the actual sum. Meaning my error on either side will be within 0.01. That's the error bound for alternating series. Now there's one more topic that we need to talk about with alternating series, and that is absolute and conditional convergence. So a series can be classified as absolutely convergent if the series of absolute values is also convergent. And a series can be called conditionally convergent if the series of absolute values is not convergent. So essentially what we're doing for absolute and conditional convergence is we're using the alternating series test on the alternating part. But then what we're doing by taking the absolute value is we're removing the alternating part and saying, hey, would this series converge or diverge if it weren't alternating? Kind of like that one on the front. We already looked at this, and this is the first example we're going to look at. Would it converge or diverge if we weren't using alternating series? Now, we can't use the alternating series test at that point. We have to come up with a different test. But would it converge or diverge? And then we get our answer. So let's look at this first example, and you'll see we've actually already done this before. So, first of all, I see it's an alternating series. Oops. I see it's an alternating series. -1 to the n minus 1. So I know it's alternating. So I can use the alternating series test. So my alternating series test says is it alternating? Yep, we've got that. Is the limit as n approaches infinity of the series without the alternating part equal to 0? And the answer is yes, so I've got that condition. Is it a decreasing series? Is 1 over n plus 1 less than 1 over n? And the answer is yes. So I know this series as it is written converges. I know this series as it's written converges. Okay? But now what I need to check? I need to check whether or not the absolute value of the series converges, which really means I'm looking for, does the series of 1 over n converge? And the series of 1 over n happens to diverge by the p series. It's a harmonic series. It diverges by the p series. Therefore, this series convergence here is what we refer to as conditional. Conditional convergence. Because it converges as an alternating series, but outside of that, it does not converge. And therefore, this is called conditional convergence. So hit pause and try the next one and tell me whether it's absolutely convergent or conditionally convergent. First of all, can we use alternating series? And the answer is yes. That much is ready to go. It's alternating. So by the alternating series is the limit as n approaches infinity of 1 over n squared equal to 0, and yes, it is. Is it a decreasing series? And we've already showed that this is in fact a decreasing series. Oops, that wasn't supposed to say n plus 1. That was supposed to say n squared. N squared. And so this is convergent. So this series as an alternating series converges. Now I need to look at this series in its absolute value form, meaning I'm rendering that alternating part useless, essentially. So is the series of 1 over n squared convergent or divergent? Well, we know this converges by the P series, because here P is 2 and 2 is greater than 1. So this converges by the P series. Therefore, my entire series here is what we call absolutely convergent. And that is how we determine absolute or conditional convergence. So there's yet another type of convergence test under our belt, and that's the alternating series. Have a good day.